That's great.
Thank you, Brian. I apologize. This is my second or maybe third talk for some of you. So I thought I'd share a little bit about something that maybe you don't know about me, is that I'm kind of a closet classicist. Does anyone know what this is a diorama of? Rome. That's right. Very good. It's an aerial view of old ancient times. So the other thing you should know about me is I like really awful jokes and typography. So with that, let's really get into what I want to talk about, which is C groups. So why C groups V2? Well, 11 years ago, a very fine-looking fellow got up here and talked about C group V1, or as we called it at the time, C groups. Now, this was so long ago, it was before what people knew containers. So I had to come up with a term of my own, which I called putting users in a box, which we would now call a container, not a container image, mind you. That's a completely different thing, but a container. And a lot of what I talked about 11 years ago about why we want C groups and why we want to contain users' jobs is still true. So I thought maybe we could quickly review that talk of mine from 11 years ago. We don't have much time, so I have to kind of go through it pretty quickly. I hope you all get this. And I think the really important thing here was on slide 4. Does anyone know? No? So maybe we need to go back a little bit and zoom in on slide 4 here and see what I was talking about. So this box or container, as I called it at the time, would need to have several properties. And we want to put our users' jobs in this box that has these properties. From the bottom up, we want to be what we call managed. That is to say, if, for example, we provision a user's job with a gigabyte of memory, we want to ensure that that user's job does not use more than a gigabyte of memory, even if it spawns multiple processes. And until we got C groups, there was no good way to do that. For 20 years, 30 years of Condor, the only way we could constrain a user's job's memory was to poll, and we did it every 6 seconds, and hope that it wasn't over, and kill the job if it went over in that polling time. But I don't know about your jobs, but our users' jobs can do an awful lot of damage in 6 seconds, or 3 seconds on average, depending on what your sampling period is. So C groups V1 at the time was a fantastic addition to let us manage these jobs more completely, which was really important as we were getting more and more cores on machines, and we had more and more, or a higher degree of multi-programming. Now, unfortunately, C groups V1 was not perfect, as many first attempts out of the box was. Now, it did give us limiting of memory and CPU and a few other things, so that was great. It did give us monitoring. So even if the memory or the CPU or what have you, the resource usage did not go over the limit, we could still measure it. And this is really important because a big problem, a big question users have is how much memory should I ask for? And a lot of times the only way to do it is to give it substantially more than it needs, run once and measure it. And that monitoring is really, really important. So we can create and destroy these. And probably most importantly, these boxes cannot be broken out of. So the users can't escape. There's these other properties here that we'd really like to have, or I wanted to have 11 years ago, that C group V1 did not give us. And sort of spoiler alert, we don't get all of them from C group V2, but we make a little progress. So you might ask, why are we doing C group V1 now? Well, it's kind of not our choice. C groups V1 came along in RHEL 5-ish. It kind of started working better in RHEL 6. So up to and including RHEL 8, we had C group V1 no matter what. And sort of if your dial of awesomeness goes from 1 to 11, you can think of C group V1 as 1. But in EL9 and sort of related distributions, we get C group V2. And while that's not perfect, it sort of turns the dial all the way up to 2. Now, It is possible to turn off cgroupv2 in EL9 and friends. Please don't do that. You'll break no ends of stuff, not just Condor, but other things. And something I think is often overlooked when we talk about what distribution cgroupv1 or v2 runs as, if there's one thing people should know about containers, maybe past it's a lightweight VM and I don't know much else. The one thing you should know about containers, if you know one thing about containers, it's that they share a kernel. So that all your containers on a machine share a kernel. And cgroups is a kernel feature. So with our delightful model of Docker here, if all these containers are different distributions, EL6, EL7, EL9, EL23, whatever, that distribution in the container doesn't control what cgroup version you have. The version of the kernel on your host that they ride on, the big whale here, that's what determines what version of cgroups you have. So this is a little surprising because all of a sudden your old EL5 containers may suddenly get cgroupv2 support, which is a little bit of a surprise. As a quick sidebar, quick note, I got this from Tim C. I don't know if he's in the audience. He's pointing me to this fantastic video about how containers work. It's 45 minutes. I don't have time to go through it. If you're interested in all, this walks you through it. It's an amazing video. If you want to know how containers work, I cannot more strongly recommend you watch that video. The notes are up. Go read that. So the best thing about cgroups is they're implemented as a Linux file system interface. So, you know, this hopefully doesn't surprise anyone. Here's a typical subset of your Linux file system. It's hierarchical. You've got directories as ovals here and files or file-like things as squares. And the cgroups just gets mounted on sysfs cgroup. So they show up in the file system, you look at them, and that's fantastic. So the root of all evil with respect to cgroups, v2, as well as v1, although from here on out, I'm just going to talk about cgroupv2. You can go into sysfs cgroup, and that's where they're mounted, and that's where they exist. Now, I have to bring up a sidebar here. Who's here has heard this, that everything is a file in Unix? I'm surprised everyone's hand's not up. Okay, everything is a file. Who here has told this to someone else? I notice Marone's hand is not up. Did you not say this in 536 when you taught it? Now, this is true in the same sense that the sort of solar system model of the atom is true, which is to say it's not true. It's a useful abstraction sometimes, but it's not really correct. If we wanted to have a somewhat more useful abstraction, maybe the point cloud model of the atom, Frank, I don't want to hear about quantum theory here. We might say a better story is that every object in Unix has a name, and this name exists in the single global hierarchical namespace. It's not an acyclic namespace, it's directed because we have symbolic links, and cgroups are in here. Does this make sense to everyone? That's kind of a mouthful. Okay, good. Now, because I just can't control myself, sidebar to the sidebar is because in Unix we have this single hierarchical namespace for our kernel, we get a great deal of power. We have abstractions, so we can have things like real files and devices and the null file and cgroups and raw memory and interfaces to the kernel that all have names, and all the same tools that we have like grep and cat and by God, Moats said, all work on these same things, and that there's a tremendous amount of power there. And my question for you that I will leave you with, I absolutely do not have time to talk about, is should we do something more similar in HTCSS? A job has a name. It's sort of nominally in the namespace of a SCED or an AP, but that's only implicit. There's no single string that describes those things. And it's a hierarchy. The SCED that the job lives in kind of lives in the namespace of a collector, but we never have a big string like that.
So why is that important that it's hierarchical? Whether the hierarchy kick in? And by the way, the way that you had the image that the root is a trunk of a tree that was just cut down is not very encouraging.
Yeah, it's interesting that the root, the file system tree is an upside down tree. So I'll let you think about that.
Yeah, but why is it important to be hierarchical? Where is the hierarchy coming in? Why is it not just a namespace?
I think it's hierarchical because sometimes you want to iterate over all the objects that are managed by a single thing. Maybe you want to know all of the jobs.
Yeah, but I can define it as a string operation on the name. I don't.
Well, let's take this offline.
If you go to the sidebars, and I'm willing to take it to offline, but you make a big deal that it's hierarchical. So I'm trying to understand where do you see because what you just said, I can do in a string operator on the namespace. It's just a convention that you say that everything that has the first 5 letters to be something, do something to it.
We could have that convention. Our tools do not support this convention today. So, for example, every time I need to refer to a job, if I want to refer to the SCED the job is, I need some exogenous way to point at the SCED in the job. There's not one convention to say.
I agree with you that having a namespace is important. I'm just challenging the hierarchical, but move on.
I think it's really important for this particular example that the AP is responsible for the names of the jobs at that AP. Nobody else gets to put anything into that. That the hierarchy here is of control of the next layer down of the namespace. And so that, yes, I'm a SCED, I report to a collector. The collector can say yay or nay to the name that I say I want to be known by. And then I, in turn, get to name my jobs. And so we don't have to manage a global namespace if we have a global hierarchy, right? It is all local control. It's all under the control of the resource owner. It's very much in accord with our distributed computing principles that we can access anything anywhere, but we don't actually have to have a single global registry that we control and worry about.
Okay, I'm not sure it's hierarchical. It's a question of a MAC address is hierarchical, or you say I own the first 10 bits of the MAC address, and I have freedom to do anything below it. It's a convention of how things are being agreed upon. But I feel that many of us, although I didn't grow up in the Unix land, I grew up in IBM land, grew up in a world as if the file system hierarchy is the best thing that happens in sliced bread. So I'm challenging it, but let's move on.
Okay, I'm really interested in this conversation. Put that down. and I want to continue it. Because this is all in the file system, if you are curious, I encourage you to play. You can make C groups with the standard commands like makedir or cat or whatever. I'm not going to go into this, but I encourage you all to, if you're interested, to experiment this way. But if there's one tool I want you to learn about, who here has used top? Yeah, top is great, except when you have a machine with 256 cores and then one line per process gets a little unwieldy. With C groups, we have the systemd cg top, which does what top does, but it does it at C group granularity. So maybe you don't get 256 lines on your old-fashioned 24-column terminal. So moving back to the file system here and the root, C groups really have two abstractions. And the first is a C group itself. And this shows up as a directory under sysfs C group in the usual Unix way. It has file system permission bits, and each C group contains 0 or more Unix processes in a tree structure. Even though this is in the file system namespace, you can't have symbolic links. So it's a strict hierarchy. It's not a graph. The group names are created by, if not users, user space, usually including systemd. And every process in the system exists in exactly one C group. You can't opt out of the C group system. So that's abstraction number one. Number two is what I can call controllers, and these appear as a file or files under each C group. And those are created by the kernel. You don't get to create controllers. And the names are fixed by the kernels. But again, they show up in the file system, and the owner is whoever created the C group. Some of these are read-only, some are read-write, some are write-only. And these provide the monitoring and the control of all the processes in each C group. One thing that's a little annoying about cgroups v2, which is why it's not at 11, is that some of the information in these controllers represents information about the sum, the aggregate of all the processes and all the C groups under it, and some do not. Which one is which? It's completely arbitrary. So for example, cgroup.procs says the list of processes in this C group. And if you're in the root C group, that's the list of all processes in the system. And if you're in an interior C group, it's always empty. So you kind of got to be aware of that. And there's 3 tiers of rules for using C groups. And the first tier is kind of like the laws of physics. And these come from the kernel in that you really can't break them and you really can't change them either unless you make a kernel pull request. One, I think, particularly tricky thing is that the Unix process tree is not necessarily one-to-one and onto with the C group tree. A very important rule is that only leaves of the C group tree can hold processes. Interior nodes cannot hold processes. And the final kernel-enforced rule is that if you want to move a process, because you can move a process after it's born to a different C group, you can move it to any other C group on the system if you can write to the target C group, you can write to the source C group, and you can write to the most common ancestor group between the two. That's a little complicated. I call it myself the arch rule because I think about moving it over an arch over the tree. Let's look at these rules a little bit in detail. So this is a leaf rule example. Hopefully that's pretty straightforward. It's a little weird for some people. But this is one of the rules of C group. The arch rule is maybe similarly better explained by graphics here. So if we want to move a process from group A1 to group B1, their most common ancestor is group A here. So I want to do this move. I see that I have to have write access to group A1, B1, and group A in the middle, the most common ancestor of the two. So those are the kernel rules for C group. Now, we all live with systemd. And this kind of gives us the next level of rules. If the kernel rules were like physics, which we can't break the laws of physics, we can't go faster than the speed of light.
Do you understand why a move between the two? What is the core of? There must be a reason for why something has to change in group A, so that a process can be moved between B1 and A1.
So as usual, you're way ahead of me. If you think about maybe we want to have a separate C group for every slot and a separate C group for every job we want to create. If we have 3 different C groups and 2 are owned by Greg and 1's owned by Doug, I want to be able to prevent, in some cases, me moving my processes from one of my job C groups to another one. The system can prevent that.
So you expect a group A to have the authority over all the processes in its siblings?
Yes.
But you didn't say that I have to have access to group B, or you assume that that is,
That's not what the rule is. The rule is, I don't write the rules. I don't
no,
write the
no,
rules.
I'm asking, the rules
I
have
think-
to make, or is the assumption that by definition I have access, does group B need to know that the process moved away from B1?
No,
Or, so there's no way for group B to prevent the process from leaving?
no, there's no way for Group B to prevent that.
But group A has the power to allow it to come in.
Yes, because presumably Group A created Group B.
Okay, so departure, there's no passport check on
Yeah.
on departure, only on arrivals.
And maybe departure arrival in the middle of the flight, I guess.
That's okay.
Um,
It happened to you on a train when you
yeah, there.
traveled, and yeah, okay.
So the second tier of rule is more like sort of human law, and this comes from System D. So you can break it, but there may be a punishment. And again, change the rules is a little bit tricky. The System D rule is that every C group subtree has one manager process that's allowed to write to it, and by default, that's System D, process one, that starts everything. And System D has some naming conventions for where things live. And to tell System D that you would like to be the manager of a certain subgroup, C group, or C group subset, you use the delegate property in your unit file. And this is what we do in HT Condor, so that when System D starts Condor as root, it puts a Condor service. And the processes here, here's 4 that I picked kind of at random, will be launched by System D into the Condor.service C group created by System D. Now, the question is, what C group should we put jobs in? Now, in CgroupV1, we didn't have all these rules, so we just put it up at the root. Now, that's kind of a problem. We can't do that with CgroupV2 because that violates the one writer rule. And also, it doesn't nest very well. So, for example, if a Condor job happened to be recursive and launch a glide in, we couldn't also write it at /Condor because that's global. So what we could do is move the job under the Condor.service and make a C group there. And that would be better because then we can recurse. If the job itself is Condor and wants to put its subjobs in a C group, we could do that, and that would nest, and that would be great. But this violates the leaf rule because our Condor daemons are in the Condor service. So how do we fix this? Well, it turns out that when we start up in System D, there's also a knob that we set now, delegate C group, which puts the actual service jobs in a sub C group of the one it creates for Condor. And then we can go up and over one and create our jobs under there. And this satisfies all our constraints. So I know that the C group tree is sort of deep and bushy and confusing, but it's because of all these rules. It's not because we want to do anything particularly tricky. So we said that by default, System D launches the daemons under Condor service, and we put our jobs under Condor and slice 1. And when we do that, we get all these controllers. As soon as we make a new C group, the kernel very conveniently launches into creates into existence a whole bunch of these controllers. Here's 6 of them that we tend to use. cgroup.procs is a read-write file. If you cat it, that's the number of PIDs in the C group. cgroup.kill is a write-only file, which Condor uses now, which atomically kills all the processes in that C group. And this is fantastic because 20 years ago, not on this stage, on this virtual stage, Todd, where's Todd? He's probably left, was telling all about the wonderful new feature of Condor where we could run jobs as the user. And Bart said, but you know, when you kill the processes one by one could fork quickly and try and escape. And I have a security hole in Condor that you can't fix. Todd, of course, had some god-awful hack, clever workaround that fixed this the next year. But now we have an atomic way to do this at the kernel with cgroup.kill. Similarly, there's memory-oriented controllers where we get byte accurate measurements of the memory used by all the processes in the C group. And we use that to populate the various attributes we see in jobs. I wanted to quickly talk about GPUs and these little feral chaos monkeys. One of the biggest problems we have using GPUs in CHTC is that they have absolutely no protection whatsoever. So any job can overwrite data in the memory of any other GPUs, even if it hasn't been granted protection to do this. And the way that NVIDIA tells us to do this is, well, you just set an environment variable, and that tells the NVIDIA libraries that it can't access the wrong GPUs. And indeed, that's true, but you know, all a job has to do is unset that environment variable, and it has access again, and it can go Fandango on core, and we've got problems. So there's a new BPF, as you may have heard by that very distinguished gentleman yesterday, giving a talk about BPF. There's a way to install a BPF program to prevent that from happening, and indeed, that's what we do. This involves no end of arcane sorcery, so we have a knob to turn this off just in case we got it wrong. I know I'm over time, but really the really interesting thing that we get from cgroupV2 is delegation. And delegation is a fancy word for just means writable C groups. So when Condor starts up, and it starts a new slot and creates a C group for a job, it chones that C group so that the job can write to it. And actually, we should do this. And what this means is that the job can then create its own sub-C groups within the C group that Condor created for it, which means that if Condor allocates a certain amount of resources, memory, CPU, whatever, the job can then use C groups to have the kernel put sublimits on while the sum of the limits still comes from the parent job. And this, we're not quite there yet, but I'm really hopeful that this will solve no end of problems when we're having glide-ins and other pilot systems. But to do this, we need support from both the local batch system and whatever glide-in system we have. The local batch system needs to make our C group writable or delegatable, and the glide-in needs to be able to start and create sub-C groups from where it is. So I'm asking you for help because to roll this out, we need support from Slurm and Kubernetes to allow glide-ins or pilots to get delegated C groups. And I want to have a special shout out to our friends from Elise at CERN because they are doing this today. So on their systems where Condor is the base batch system, they're running Condor 23.8, which has this support. And their pilot system, is it Durac? They have their own thing. Yeah. What's that? Alien. So Alien, pains me to say, Alien is ahead of Glide and WMS in this one regard, in that it creates sub-C groups, delegated C groups, when it's running on a Condor system. And the Elise people have some arcane configuration with their Slurm system that enables us in Slurm as well. I would love to see us come to consensus on what the right way to do this with Slurm and Kubernetes so we can get this everywhere. So I apologize for going over. I swear it was not my fault. There's about, if there is time for questions, I don't know if there is, I'd be happy to take them, or we can talk during the break. Thank you very much.